Good day, everyone. Today I'll be discussing on digital image processing. And within digital image processing as a course, I'll be talking about image classification using KNN neighbors. Let's look at the outline for this presentation. The part 1 talks about the KNN concepts, which includes introduction to image classification, what is KNN neighbors, how the KNN neighbor algorithm works, different metrics for calculating distance between points, the number of neighbors, the pros and cons. The part 2 of this presentation includes implementation of KNN in MATLAB. And we'll start off by discussion on the various KNN algorithms, such as the discrete value target function, the continuous value target function, the distance weighted nearest neighbor algorithm, and implementation steps of KNN in MATLAB. KNN concepts. Let's start with part 1. Introduction to image classification. Image classification in digital image processing refers to the process of segmenting images into different categories based on their features. A feature could be the edges in an image, the pixel intensity, the change in pixel values, and many other features. The intent of the classification process is to categorize all these pixels in a digital image into one of several classes or themes. Normally, multispectral data are used to perform the classification, and indeed, the spectral pattern present within the data for each pixel is used as the numerical basis for categorization. Image classification refers to the labeling of images into one of a number of predefined classes. The goal of image classification is to identify and portray as a unique gray level or color, features, structure, or pattern occurring in an image in terms of the object these features actually represent on the ground. The need for automated classification arises from elimination of human error and saving costs when classifying large volume of data. The two main types of image classification are supervised and unsupervised classification. There are also different image classification techniques used in digital image processing, such as the minimum distance classifier, the maximum likelihood technique, etc. What is K-nearest neighbors? K-nearest neighbors is one of the many supervised learning algorithms used in digital image processing, data mining, and machine learning. It is a classifier algorithm where learning is based on how similar a vector is from other data. K-nearest neighbors have been used in statistical estimation and pattern recognition since the 1970s. The KNN algorithm assumes that all instances are points in some n-dimensional space and defines neighbors in terms of distance. The KNN algorithm classifies unknown data points by finding the most common class among the k closest examples. KNN determines the decision boundary locally. This is done by assigning each image pixel to the majority class of its closest neighbors, where k is a parameter. The k in KNN refers to minimum distances of image pixels that are to be considered for classification. The rationale of KNN classification is based on contiguity hypothesis. This means that we expect the test image to have the same training label as the training image pixels located in the local region surrounding the image. KNN algorithm is also called instance-based learning, memory-based learning, example-based learning, lazy learning, etc., among various professionals in different disciplines. Let's look at how the KNN neighbors algorithm works. The KNN algorithm is pretty simple. If there are three sets of points, if three sets of points are given on an XY plane as shown in the diagram on the right, as you can see, the input consists of a set of endpoints, each labeled with y distance classes. In this case, our y is 3 based on the image green, yellow, and red points. These labeled points correspond to the training set. The KNN algorithm uses the training set to learn the classes of a new point. The choice of a class to be assigned to the unlabeled point depends on the distance between the respective labeled points and the new point to be classified. And you can see in the image, you first look at the data, calculate distances between the new points you want to classify and the labeled points in the image. You find the neighbors based on the distance between the new point you want to classify and the other existing points in the image. And lastly, you vote on the labels, depending on the highest occurring label. The different methods for calculating distance between points. Each point in the KNN two-dimensional space example shown in the previous page can be represented as a vector. A vector is a list of two numbers. All these vectors packed vertically form a matrix representing all the points in the two-dimensional plane. To calculate the distance between these 2 points, in our case, pixels, which are used as sample or training, and all the pixels in the image, which forms a test set, is actually simple. There are several ways to get this value. Some of them are shown in the image on the right. Most of these distance matrices were designed for linear or real valued attributes. As you can see, we have a Minkowski distance, the Euclidean distance, the Manhattan or city block distance, the Canberra distance, the Chebyshev distance, the Mahalanobis distance, the correlation, chi-square, and Kendall's-Rag correlation. The number of neighbors. KNN is a minimum distance classifier. The KNN algorithms decide a number k, which is the nearest neighbor to that data point, which is to be classified. If the value of k is 5, it will look for 5 nearest neighbors to that data point. If the value of k is 1, it will just select the nearest point, the significance of k. If the value of k is small, then the result will have a higher noise dependency. If the value of k is bigger, the confidence in the prediction increases. But decisions can be skewed if k has a very large value. A popular rule of thumb is to select k to be less than the square root of n, where n is the number of training examples. The pros and cons. The pros or advantages of KNN. KNN works well on many practical problems and is fairly noise tolerant depending on the value of k. It can use more complex or symbolic representations. It requires little tuning and often performs quite well. The cons or disadvantages of KNN. KNN is subject to the cost of dimensionality, that is, the presence of many irrelevant attributes. KNN needs additional distance or similarity measure that match a target function. The prediction accuracy can quickly decrease when number of attributes grows. For large training sets, the KNN must take a pass through the entire data set for each classification. This can be prohibitive for large data sets. In part 2, we have the implementation of KNN in MATLAB. First, we start with discussion on the various KNN algorithms. The focus is on using MATLAB to effectively classify an image using the KNN algorithm. The typical classification involves storing all the training examples, xi, and their classes, xi, calculating the class xq for a given instance sq using each k nearest neighbors. When the nearest neighbor is 1, locate the nearest training example xn and estimate class sq as sq being a function of xn, k nearest neighbor. locate the k-nearest training example, and estimate class SQ using majority vote among class values of k-nearest neighbors. The test example is classified based on the majority class of its nearest neighbors. Discrete value target function. For functions using discrete value data, the KNN algorithm returns the most common value among the k-training examples nearest to it. The algorithm are the training algorithm. For each training example x, which is a function of x, add the example to the list of training examples. What this simply means is, if we have data containing a training example, we should put the training example in an array with its data and label. Classification algorithm. Given a query instance SQ to be classified, let x1 to xk be the k-training examples nearest to SQ. What will return is a function SQ, which is the maximum argument in the summation of the deviation of v and the function xi, all within the interval k and I equals 1. Where the deviation of a comma b is equals to 1 if a is equals to b, and the deviation of a comma b is equals to 0 otherwise. Continuous value target function. The KNN neighbor algorithm is easily adapted to approximating continuous value target functions. To accomplish this, the algorithm calculates the mean value of the k-nearest training examples rather than calculate their most common value. The formula is as shown below. The function x of q is the summation of the function of xi over the interval k and I equals to 1 all over k. These continuous value target functions are normally encountered with KNN is used for regression problems, whereas the discrete value target function is used when KNN is used for classification problems. The distance weighted nearest neighbor algorithm. One obvious refinement to the k nearest neighbor algorithm is to weigh the contribution of each of the k neighbors according to their distance to the query point SQ, giving greater weight to closer neighbors. The distance between two instances, xi and sj, is given as the xi, sj, where the xi, sj is equal to the summation of the argument of xi minus argument of xj all squared within the interval n and y equals 1. And if we define a weight parameter, the di, to be equals 1 over the sq over xi all squared, then for a discrete value instance, the formula will change considering the weight parameter. The formula becomes f of sq becomes the argument of the maximum argument of weight I, the deviation of v, comma, f of xi within the interval k and I equals 1. For the real value instance, that is the continuous value target function, the formula will change as well to f of xq will now be equal the summation of which I to the function xi in the interval k and I equals 1 divided by the summation of which wi over the interval k and I equals 1. KNN implementation steps in MATLAB. For us to implement KNN in MATLAB, we have to take these 10 steps. First of all, we'll read in an image and initialize classes and training set size. We select training set sample regions from image. We look through the selected sample regions and display the regions. We convert the RGB image to a lab image and extract the A and B components. Next, we calculate the mean of the A and B components of the training set sample regions. We initialize parameters for calculating the distance. We calculate the minimum distance between the sample regions and the test set, which is the entire image, using the equivalent distance matrix. We display the reclassified image. Then we initialize the scatter plot for the nearest level classification, and we plot the values utilizing the standard plot parameters. So after listing these steps, we can now go over to MATLAB and implement these steps. This is our MATLAB window. I'll create a new script. I like working with scripts. I can write my code. Next, I will navigate to my folder that contains the images which I will be using. I'll just give you a heading, image classification using KNN. So we'll start from step 1. Step 1 says read the image and initialize classes and training set size. So we are going to read an image and initialize the training set size. We use the imRead function to read the image. imRead, our image is called ball.jpg. That is our image. We will show the image. After showing the image, we'll get the size of the image, and we'll call this size. We'll assign the size of A to the variables B, C, and D. So let's read in our image to see what we are working with. Okay, this is our image. As you can see, our image has 1, 2, 3, 4, 5, 6 balls with different colors: the red, orange, yellow, blue, pink, green, and the background. So what we're going to do next is to initialize the classes that we're going to classify the image. So create a variable classes, red, orange, red, orange, yellow, blue, yellow, blue, yellow, blue, pink, green, and background, which is white. Pink, green, and background, which is white. So we have initialized the classes that we have in the image. Next, we're going to get the number of classes, which is using the length function, the length of the classes. The length function gives us the number of items we have in the class variable. As you can see, the number of classes is 7. So we'll move over to step 2. Step 2 says select training set sample regions from image. So we're going to select sample regions from this our image. And in doing that, we are going to use a function called ROI poly. But before then, we need to initialize some values. Then we'll look through our number of classes. For I equals 1 through number of classes. Number of class. Then we'll set our F, name of the class, to be select sample regions for classes. We'll look through the classes. And for us to we also need to for us to look through this, we also need to initialize our training sets. We'll use the size of the original image, B, C, and the number of classes as the image. So this is our training. So after setting what the title will look like, we'll now look through our image by using the ROI poly function. So after that, we'll now close our figure. So let's select our figure. Sorry, this is supposed to be semicolon, not colon. Okay, so we can select a region by making the polygon on the image. Make sure that is a polygon. Go over to the next color. Double click it. Select the region. Next, blue. Go over to the pink color. Or go to the background. So we have been able to successfully select our sample regions from the image. The sample region is our training set. So next, we are going to look through, we are going to display the sample regions we just selected by looking through the image. And that should be step 3, which is look through the selected sample regions and display the regions. So we'll call it step 3. So for step 3, we'll look through from height to number of class again. We want it in a new figure window. We'll use our IM show function. And we'll look through the training, all the classes in the training. Then we'll set to a title. Sample regions for our classes. End it. So let's display the sample regions chosen. Sorry, should have put from 1 to the number of classes. It's only displaying the background. We want to display everything. Yes, as you can see, the sample region for background, sample region for the green, sample region for pink, and you can see that there are logical images, 0 for regions outside and 1 for regions within the image. For blue, for yellow, for orange, for red. So we'll move over to step 4. Step 4 says convert the RGB image to lab image and extract the A and B components. So we'll convert our entire image into a lab image. And we'll do that using the function sRGB to lab. We use this function make form to convert the image of sRGB to lab. So our lab image will now apply to the image using the form we just created using the make form. After that, we display the image that we just created, that we just converted. So let's convert this image to an RGB, to a lab image, from RGB to lab. As you can see, this is our lab image. Now, a lab image has 3 components. The first column is about the brightness of the image. The second column is the red and blue, the reddish blue components of the image. And the third column is the greenish blue component of the image. So we are not interested in the brightness of the image for this classification. We're only interested in the color. So we are going to be using the second and the third column. We're going to be extracting the second and third column, which is the column that we need for the color classification. Like I see, we extracted this. I want this to obtain our components. Okay. So step 5. Let's go back and see what step 5 says. Calculate the mean for the A and B components of the training set sample regions. Okay, so we are going to be calculating the mean of the sample region. Meanwhile, in calculating this mean, we first need to create a matrix that will house the mean. And we'll call that matrix column markers. And these column markers will use a representation matrix of zeros, number of classes, and 2 columns to represent our column markers is now the matrix is a 7 by 2 double. So we can go ahead and calculate the mean for the training samples. Indeed, we are going to use a for loop where it iterates through our number of classes we take everything on the row, take first column, we'll use the min2 function to get the mean. We close it into our lab image. I feature it. For the second column, these are column markers again. Everything on the row. And the second column, this time we are going to be using bx contains the second column. We're going to iterate into the last So by doing this, we have calculated the mean of the A and B value. You can see we have calculated the A and B values for the training region. The mean of the A and B values of the training region using column markers. Step 6. Step 6 says initialize parameter for calculating the distance. So step 6, initialize the parameter for operating the distance. And first of all, we're going to be changing our color labels to be between 0 and our number of class -1. This is because our sample regions are logical 0 and 1. So by taking the sample regions through 0 and 1, we can be able to extract the labels at each of those regions. We convert our lab components to double. Then we'll create our distance matrix, which is a representation matrix, zeros, and the size will be size of one of our components of lab image, and the columns will be our number of classes. We are going to initialize all the parameters, calculating our distance. So step 7 says calculate the minimum distance between the sample regions and the test set, which is the whole image, using our collision distance metric. So our step 7 will be to calculate the distance between, and we'll use a for loop for that. Okay, through the classes. Square root the whole image, and as the training, which is in the column markers. Subtract the first column, then square it, we'll add it to the second column, the subtraction of the the second column, we'll also square it. We just implemented the formula for hidden distance, which is the square root of x1 minus y1 whole squared plus x2 minus y2 whole squared. So when we run this, we'll be able to extract the distance from it. Then we can easily remove the value and the label from our calculated distance. We first find the minimum of those values for our distance along the third dimension. And now we'll extract our label from our color labels which we defined earlier. So you can see we have been able to extract our labels from our distance. Let's go back to our presentation. Step 8 says display the new image classified. Okay. In displaying the new image, first of all, we need to get back our labels. I'll return them to being 7 parameters, from 0 to 6 to 1 to 1 to 7 as before. So we initialize our classified image. Initialize it to zeros using the size of our original image. So we now want to return our colors, which was already there in the original image. We know that our original image, the first color is red, and red is represented by 255, 0, 0. For orange, let's represent it as 0, 0, 255, 0, 255, 255. Our yellow is 255, 255, 0. Our green, our blue is 0, 0, 255. Our pink is 2550255. Our green is 02550. And our background, which is white, is 255255255. After initializing this, if we are ready to display our image, we have for use a for loop, we are looking through the same size as our original image, which has 55 rows, and for the columns, our classified image for our row, column, and third dimension is the color channel. We now index into colors using our labels. After looking through, we are ready to show our image. So we'll take another figure. I am sure. We'll have our color bar. So by running this code, which is the loop we have earlier created, we can see that our classified image is here. You can actually notice that it's a little bit noisy. Some colors are overlapping, and that is because we are using our n to be equals to 1. For the orange, it's not correct because the color we used is actually magenta, not orange. But overall, our image has been classified. Next is to display the scatter plot for the nearest neighbor classification, plotting the values utilizing the standard plot parameters. I already have a function written out for that, so I just pasted it here. Let me go through it. We are initializing a plot for the nearest neighbor. I created a color purple, which has 119/255 for the red channel, 73/255 for the green channel, and 152/255 for the blue channel. I created also gray, which has 200 over 255 as red channel, 150 over 255 as green channel, and 100 over 255 as blue channel. Then I plot it using the lab coordinates A, X, and BX. As you can see, this is scatter plot of our classification. You can see that the colors have actually been separated to a very large extent, identifying each object in the image. So that was the implementation of the KNN in MATLAB. And finally, I want to thank everyone for watching this video. See you next time.